Good afternoon, everyone. I'm here to talk about mostly the state of WebAssembly because Node.js and WebAssembly are related because of V8, because WebAssembly is on Google Chrome. My name is Tomé Vardasca. I work as a full-stack developer with .NET Core and React at a company called Oficina here in Lisbon. And WebAssembly, what it is, why it was created. It is a new standard developed first by Mozilla, then joined by Microsoft, Google, and Apple. It's not a programming language, as most people think it is. It's mostly a portable compilation target. I will show you later how it works. It's really compact, really portable for the web, because earlier in the history, I will talk later, you could compile from another language to JS, and the files would get really, really big. You have to wait like an afternoon to play a game, and with WebAssembly you don't need that. And then it's fast to load and runs safely, and it's near native and has near native performance. The history. The key person behind the key mind behind WebAssembly was the same mind that created JavaScript, was Brendan Eich. But everything started when I think he was like CTO or CEO of Mozilla with an internal experiment with ASM.js. They tried with a limited subset of JavaScript to make it really, really, really fast. So at Mozilla, they started privately with ASM.js to try to have like native performance in the browser. Then Google came in with Chrome, and they tried to create this new, it's not actually a plugin system, but at the time it was seen by one. It was an ACL. They created all the security primitives, networking primitives for them, but it didn't work out as they wanted to, because no other browser tried to use it. Then in 2013, Mozilla published ASM.js and also published the project that most people know, that is like a compiler between C and C++ to ASM.js. The first game they created was Banana Bread, and then they made like a joint venture with Unity, and they launched the game in the browser. It was the first game. And then in 2015, they started to make prototypes with ASM.js to create WebAssembly. There's actually a polyfill to run WebAssembly code in ASM.js. So, the applications of WebAssembly is to go, it's too loud. The main application is to go where JavaScript falls short. Most of it is performance, and to leverage our old code base, our old C++ code base. Then the other application is you can develop in whatever language you want. You can almost do it right now because you have Elm, you have TypeScript, you have Flow, you have everything like that, but you can use C in the browser. But with this, we can't. You can develop games, we can develop image and video processing. You can have security libraries running in the browser to do all the encryption stuff, and without having performance issues. You can have data processing, machine learning, and everything. So the main goals was to be efficient and fast, to be safe, because at least as safe as JavaScript. And they wanted to be open and debuggable, just to see, because if you want to have something fast, we need to see under the hood. We need to see how it's running. And another thing, it must be part of the open web platform. JavaScript most of the people say it is awful, but it is awful for like 20 years, so it's not that awful. So this is a basic example of WebAssembly. This is a C code. Then there is a text representation of WebAssembly. They have like, it's not like assembly because they have primitives for ifs, for loops, and they are like an abstraction of assembly because for it to run in every machine that JavaScript runs, it can't have like the low-level things assembly has. And then there is the binary encoding, because if you want to be it as fast and as tiny as possible, you need to have a binary encoding that is as tiny as possible. For it to be efficient and fast, they developed the virtual machine of WebAssembly as a stack machine. They don't use an AST, so if you look at the code, at the WebAssembly code, it is executed sequentially. So they can, there is an article from Mozilla where they compile it with a stream because everything is sequential. In the upside corner, there is a performance comparison between an animation with WebAssembly and with JavaScript. The gains are huge. And all the instructions are explicitly typed, and there is no overloading rules. So there's only a single pass to interpret everything. You don't need to do multiple steps like you do in an AST type language. So as I talked before, it is encoded in a size in a binary format to be as tiny as possible. And so it can be used in our phone, for example. Then it is safe. The security is by the same guys that work in ACL on Chrome, so it's really safe. And most of the time it's executed inside the JavaScript VM, so it's as safe as the JavaScript. It's pretty safe. To be open and debuggable, just like I told before, you can just see, it's like when you go to LLVM and try to see what kind of assembly it's generated. Sometimes there is a bug on the compiler, and for you to see it, you need to pretty print it. It's not the right programs by hand. I think nobody does that. And part of the open web platform, the versionless, actually in the web, the HTML is version, but nobody thinks about it. No matter it is HTML1 or 5 or ES5 or ES6 or ES 2017. Nobody cares about it. And they designed WebAssembly to look at that. Everything, it works like in JavaScript. You have to test every feature if it's there or not. And another thing, they want to integrate everything with JavaScript, everything with every browser web APIs like the DOM and everything. And they can also support non-web embeddings. So like Node, for example. The current state, every browser I think it was on 2016, in the last 2 years, they implemented the first version. And it is also the actual version. There is not a new version. I said earlier that there wasn't versions. There is versions on the specification, not in actually the language to be executed. There is a polyfill also for ASM.js, but most of the tools to work with to work with WebAssembly are really unstable. I was pretty sure they were unstable, but not so much as they are when I was preparing this talk, because for the roadmap, they want to introduce threads. They want to have also a garbage collector to use dynamic languages. They want to use shared memory, because a thing I didn't talk before, that's why also WebAssembly is so fast. WebAssembly has like a flat memory, like a flat array. It's as fast as you can to go through memory. They want to have dynamic linking, fixed with SIMD, instructions with multiple data. They tried to introduce that to JavaScript, but the community didn't want it, because now there is WebAssembly. They want zero-cost exceptions. There is exceptions right now, but you can look at the link below, everything they want in the future. There are some useful links where you have like a code editor online where you can paste some C code and see what it does and see what kind of code it generates. Now I'm doing a demo. Demo has 4 parts. I write the same program. It's just calculating a factorial of like 50,000. I write it on plain JavaScript with an interactive loop, with recursion. I will show. I write it in native Rust with an executable in Rust. I write it with Node.js. It is the most used library for native modules on Node.js. And then I write a WebAssembly module with the same code. It's actually the same. I'll show. First is it's really simple. I just have a bunch of console log with times, just for you to see the difference in time. Go to. If you can see it, they take like 4 milliseconds and less than milliseconds when you use an optimization with the last 100 calculations. And with the recursive one, the call stack size was exceeded. It was on purpose, because there are some limitations on Node how you can create new stacks. And then I will show you how it works in Rust. No, thank you. So the factorial in an interactive way, it's it's not way faster. It's a little bit faster than JavaScript. It's like half a millisecond faster. It's not statistically significant because it's only one execution. Then I have like almost a second using an iterator. Using recursion is pretty fast, but 69 milliseconds, it's pretty slow. And then I'm using a factorial with iterators, but with parallelization, just to test it out if it's faster or not. But as you can see, it's not as fast as an iterative way. This is the code for in Rust with all the functions. It's really simple. I just use the print line in the end just to show you. Now I will execute the neon bindings. The big bummer about using neon as to create node modules is you have to have this boilerplate code to interface with JavaScript. It's not that pretty. It's not hard, but it isn't pretty. I have to change a lot of code to make it work. And as you can see, the iterative way sorry, I missed this is the way. That was the final result. So. Using in an iterative way, it's really fast. It's as fast as in native Rust with its module, but it's almost the same result as with native Rust, but with the overhead to communicate with Node. And then in the end, I will show you the previous one. To compile from Rust to WebAssembly, I'm using a WASM web bind from Mozilla. It's not that stable. Right now, it only works if you compile the Rust code in release. It doesn't work in debug. I don't know why they have a bug. When I try to compile, with WASM, it's fast, but it's not as fast as the previous one, or it is as fast as the previous. It's not that faster from JavaScript. JavaScript was 3 milliseconds, I think, or 1 millisecond, but this one just half the factorial, and the recursion is on par with the Rust code. And then the last one, the parallel, failed because there aren't threads in WASM. That's why it fails. It compiles. It's a thing I think it shouldn't do, but it does. It compiles, but it just gives me an error when they try to get the current number of threads or something. So the code, the code is really simple. It's almost as similar as the Rust native one. I just used the annotation was bindgen. That's it's the best thing about doing the code this way. I think it's the only advantage, because the performance gains you have, I don't think you should first look at your JavaScript code, because there are so many optimizations on the virtual machine that you don't need to go just now to WebAssembly. So the final remarks. WebAssembly is not a programming language. You can program with it if you want it. It's almost as you can program in binary in your computer, but nobody does it. The main goals, it's native performance and safety. There are also the other ones, but it's the main ones. The future looks good, but the ecosystems are really, really young. The first version of WebAssembly came like 2 years ago, but I think we need to wait 2 more years from now to have it as stable as it can get. And my main recommendation in this talk is, for now, if you need to just look at your JavaScript code to make it as fast as possible. And if you need to spin out something, just create a native module for now, because WebAssembly, it's not ready yet. Yeah, thank you.